The void between the stars is usually silent, a vast expanse of darkness where light travels for billions of years without interruption, carrying whispers of ancient stellar births and deaths. Yet, in mid-2025, that silence was broken by the arrival of an interstellar visitor unlike any humanity had ever observed. Designated 3I Atlas, this object was hurtling through the inner solar system at a staggering speed of 137,000 miles per hour, crossing the gulf between distant star systems with an urgency that felt almost intentional. Observatories worldwide had been tracking countless comets, asteroids, and minor planets, but none presented such a perplexing combination of mass, trajectory, and chemical signature. In exactly 48 hours, this enigmatic traveler would pass within 29 million kilometers of Mars, a distance that seems safely remote by human standards, yet, when viewed in cosmic terms, placed it on a path that could reveal secrets hidden for billions of years. From the first detection, 3I Atlas defied categorization. Amateur astronomers captured its strange hues, shifting from deep red to bright green overnight, while professional telescopes measured gas plumes dominated not by water, as would be expected in a conventional comet, but by carbon dioxide at an extraordinary ratio 16 times more extreme than any known comet. More shocking still was the detection of pure nickel sublimating from the surface, without the accompanying iron that is universally found in cosmic bodies. This chemical anomaly, a signature impossible in natural star-born processes, sparked debates across observatories and research institutions. The Very Large Telescope in Chile, Hubble, and the James Webb Space Telescope all recorded data that strained the boundaries of accepted astrophysics. Observers compared trajectories, noting that 3I Atlas followed a near-perfectly retrograde path aligned with the ecliptic plane, threading through the solar system in a way that reduced the probability of random arrival to 1 in 500. The object's sheer mass compounded the enigma. Calculations suggested a nucleus at least 5 kilometers across, containing roughly 33 billion tons of material. Despite massive outgassing, the trajectory deviated by less than 15 meters per day squared, an observation incompatible with ordinary comet physics. The statistical improbability alone finding such a massive aligned object before cataloguing thousands of smaller interstellar visitors challenged conventional models of cosmic distribution. Every new observation layered complexity upon mystery, forward, pointing dust halos, anti-tails, and chemical signatures that suggested a history unlike anything seen in the solar system or the wider interstellar medium. Scientists and amateur observers alike were drawn into a web of anticipation and philosophical unease. Was this simply a relic of ancient stellar processes, a comet formed in a distant, cold molecular cloud, or did its behavior suggest something more deliberate? The window of observation was narrow, with 3I Atlas approaching perihelion and set to vanish behind the Sun for 2 months at its brightest, most revealing moment. Within this fleeting interval, humanity stood at the precipice of knowledge. Whether natural or artificial, the object demanded reflection on the fragility of assumptions, on the limitations of observation, and on the silent possibilities that lurk in the cosmos, waiting for a moment to challenge understanding itself. It was here, in this liminal space between certainty and unknown, that the story of 3I Atlas began, drawing the universe's quiet into a crescendo of anticipation, mystery, and profound wonder. The story of 3I Atlas's discovery begins not with alarms blaring in mission control, but with careful, meticulous observation from some of the world's most respected instruments and the sharp eyes of dedicated astronomers. Avi Loeb, a Harvard astrophysicist who previously stirred controversy over Oumuamua, was among the first to recognize that this object was unlike any ordinary comet. On his scale of potential technological origin, he rated 3I Atlas a 6 out of 10, signaling a 60% probability that this interstellar traveler might not be entirely natural. His assessment was grounded not in speculation, but in hard data from the James Webb Space Telescope, Hubble, and the Very Large Telescope in Chile, each providing detailed spectral and visual observations. Webb, on August 6th, revealed a gas plume overwhelmingly dominated by carbon dioxide with a paltry fraction of water, a composition 16 times more extreme than any comet previously studied at similar distances from the Sunday. Such readings challenged conventional understanding, as comets are expected to form in icy, water-rich regions, and their outgassing typically reflects this primordial composition. The Very Large Telescope made an even more confounding observation. Streams of nickel were sublimating from 3I Atlas, but with no iron in sight. Nickel and iron are cosmic twins, forged in stellar interiors and expelled together in supernovae, and they condense into interstellar dust in predictable ratios. Finding one without the other is unheard of in natural space objects. Avi and his colleagues were quick to note that such a chemical signature mirrors industrial-grade alloys produced in human technology, raising questions about the object's origin. What exacerbated the mystery was the exponential increase in metal emission as the object approached the Sunday. From July to August, nickel output surged 25-fold, an anomaly in cometary physics where outgassing follows a predictable, relatively gradual increase under solar heating. Each data point, precise and independently confirmed, added layers of astonishment and unease. Even as the scientific community debated, amateur astronomers around the globe began sharing images that confounded expectations further. Using telescopes comparable in power to small professional observatories, these hobbyists captured 3I Atlas with remarkable clarity. Their photographs displayed structured cores beneath diffuse gas, defined edges, and geometric features that a typical comet simply would not possess. Michael Jagger and Gerald Raymond, observing during the total lunar eclipse on September 7th from Namibia, documented a greenish glow with bluish tints, an abrupt departure from the reddish hues previously recorded. While professional astronomers raised concerns about tracking errors, atmospheric distortion, and instrument artifacts, no follow-up with larger scopes was conducted to verify or falsify these extraordinary observations. The dismissal only deepened the intrigue, revealing a tension between formal protocols and the raw, unfiltered insights of dedicated amateurs. Amid these findings, the implications of the October 3rd Mars flyby loomed large. This event, when 3I Atlas would pass within 29 million kilometers of Mars, promised the first opportunity to directly measure its size, composition, and possible structure with instruments on orbiting spacecraft. The anticipation was heightened by Loeb's calculations, suggesting that if a nucleus larger than 5 kilometers were confirmed, the natural comet explanation would collapse entirely, challenging assumptions about the frequency and size distribution of interstellar objects. In this delicate balance of observation and speculation, the discovery of 3I Atlas forced a reckoning within astronomy. A single object, detected quietly at first, now poised to redefine the boundaries of science, inviting questions that reached beyond chemistry and physics into the realm of cosmic intent and technological possibility. The first shockwaves rippled through the scientific community when spectroscopic data revealed the sheer impossibility of 3I Atlas's chemical makeup. Nickel, streaming from the object's surface in clear, unambiguous emission lines, appeared without its cosmic counterpart, iron. Across the entire catalogue of known meteoritic and cometary samples, from the icy fragments of the Oort cloud to meteorites that fell to Earth, nickel and iron have always been found together, forged in tandem within dying stars, and expelled into interstellar space in a balanced partnership dictated by nuclear processes. The universe has never produced one without the other. Yet here was 3I Atlas, defying what had seemed an immutable rule of cosmic chemistry. Scientists faced an intellectual dissonance. Either fundamental principles of star formation and element synthesis were flawed, or this object originated from something entirely outside the natural order, an engineered anomaly in the vast, indifferent cosmos. The pattern of impossibilities only deepened. Alongside the Nickel Anomaly was a plume dominated by carbon dioxide, a volatile component that should have been present in far smaller proportion to water ice. The observed ratio, 95% CO₂ to just 5% water, was 16 times more extreme than any known comet at this distance from the Sun. Comets form in the icy reaches of young stellar systems, their composition reflecting the primordial mix of hydrogen, oxygen, carbon, and nitrogen frozen over billions of years. To encounter an object with such reversed chemistry suggested either a completely alien formation environment or prolonged exposure to conditions that radically altered its surface composition during interstellar travel. Each of these possibilities challenged astrophysicists to reconsider the universality of what had been long accepted as typical cometary behavior. Compounding the puzzle, amateur astronomers documented shifts in the object's color and apparent morphology. Initially a deep red, 3I Atlas transformed to an emerald green overnight, glowing with a tinge of blue. While green comets are known, their color derives from diatomic carbon molecules absorbing ultraviolet sunlight and re-emitting green light. Yet, prior observations from Kitt Peak Observatory had shown 3I Atlas to be remarkably depleted in diatomic carbon, the exact molecule responsible for this photochemical effect. The green glow could not be easily reconciled with the known chemical inventory, prompting speculation about rapidly increasing cyanide and other volatile compounds as a possible mechanism. The rapidity and scale of these changes signaled an unprecedented level of chemical activity, one that did not fit the gradual outgassing models derived from centuries of comet observation. Trajectory data added a geometric layer to the astonishment. Traveling on a retrograde orbit inclined only 5 degrees off the ecliptic plane, 3I Atlas threaded through the solar system in near-perfect alignment with planetary orbits. Statistically, a randomly arriving interstellar object should intersect the inner solar system from any angle, yet this object's path reduced the odds of coincidence to 1 in 500. Its precise approach toward Mars, Venus, and ultimately Jupiter suggested either an extraordinary alignment by chance or the meticulous design of a navigated object. Non-gravitational forces, typically evident in comets due to asymmetric outgassing, were nearly absent, indicating a mass far greater than expected for its observed brightness, a solid 33 billion tons, resisting deviation even while releasing copious gases. Each anomaly, the chemical impossibilities, the color shift, the anti-tail pointing sunward, the improbable trajectory, and the massive, steady nucleus layered upon the others to create a singular scientific shock. Researchers faced a paradox. All known physics seemed insufficient to fully explain the phenomenon. Either humanity was witnessing a natural object with properties that stretched the boundaries of interstellar physics, or, more unsettlingly, an artificial object had entered the solar system, carefully designed to confound and intrigue. The shock was intellectual and philosophical, forcing astrophysicists, chemists, and astronomers alike to confront questions they had never anticipated, and in doing so, it redefined the parameters of what an interstellar visitor could be. Amid the cascade of anomalies, the chemical composition of 3I Atlas demanded scrutiny, not merely for its peculiarities, but for the profound implications it carried about the object's origin. Observations from the James Webb Space Telescope revealed a dominance of carbon dioxide, a volatile 16 times more extreme than any comet previously recorded at similar distances from the Sun. Water, which defines the behavior of conventional comets, was a minor component, comprising a mere 5% of the volatile composition. This inversion of expected ratios was not a subtle deviation, it was a categorical upheaval of what scientists understood about the formation of icy bodies. Comets originate in the cold outer reaches of stellar systems where water ice forms readily and dominates the volatile content. For 3I Atlas to manifest as a dry ice ball with minimal water suggested formation in a radically different environment, potentially a protoplanetary disk with a markedly unusual temperature and chemical profile, or exposure to billions of years in interstellar space that altered surface chemistry in ways conventional models cannot predict. The situation grew even stranger when telescopes measured the presence of nickel in the outgassing plume. Nickel sublimating without its natural partner, iron, represents a phenomenon without precedent in observational astrophysics. In every known stellar and planetary formation process, nickel and iron are co-synthesized within massive stars and expelled together during supernovae, condensing into asteroids, comets, and interstellar dust in predictable ratios. The absence of iron alongside nickel in 3I Atlas cannot be accounted for by ordinary cosmic mechanisms. Industrial processes on Earth routinely separate nickel from iron to produce high-purity alloys used in aerospace, electronics, and battery technologies. While it is not definitive proof of artificiality, the spectral signature's resemblance to engineered nickel was deeply troubling and unprecedented, raising questions about whether natural astrophysical processes could ever yield such an outcome. Adding to the puzzle, the rate of nickel outgassing increased exponentially as the object neared the Sunday. In July, at approximately 3.9 astronomical units, the emission rate was significant but not extraordinary. By late August, at 2.85 astronomical units, the outflow had surged 25-fold. This sharp increase did not conform to the gradual thermal response observed in standard cometary outgassing, where heating drives predictable sublimation of volatile compounds. Instead, the pattern suggested a highly reactive surface, or an engineered process, systematically releasing metals in proportion to solar exposure. Cyanide, hydrogen, and other compounds were also being emitted in quantities and at rates unprecedented in interstellar objects, correlating with observed color shifts from red to green in the visible spectrum, potentially linked to photochemical reactions or thermal processing of surface materials over billions of years. These chemical anomalies forced a reconsideration of the object's provenance. Could 3I Atlas be a natural relic, a fragment of a distant planetary system altered over 7 billion years by cosmic rays, collisions with interstellar dust, and near absolute zero exposure? Or did its behavior hint at deliberate engineering, a structure designed with materials and chemistry to withstand interstellar travel while exhibiting behaviors that challenge natural explanations? Each piece of data, the CO₂ dominance, the lack of water, the nickel without iron, the cyanide spike, and the dynamic color transformation compounded the mystery. It became increasingly clear that 3I Atlas was not just another comet. It was a test of scientific assumptions, a probe into the limits of what humanity could explain, and a challenge to the boundary between natural cosmic phenomena and technological design. Observations scheduled for early October during the Mars flyby promised to clarify these questions, yet the object's secrets remained tantalizingly, frustratingly, just beyond immediate reach. As September waned, 3I Atlas began an act that only deepened its mystique. It disappeared from view, slipping behind the Sun from Earth's perspective. For nearly 2 months, ground-based telescopes lost all line of sight, unable to observe the interstellar object during its brightest and potentially most revealing phase. This period coincided precisely with perihelion, its closest approach to the Sun, when comets typically exhibit peak activity driven by intense solar heating. Outgassing rates, dust emission, and surface transformations are maximized at this point, offering the clearest window to study composition, structure, and any underlying activity. The timing, however, seemed almost deliberately opportune, as if the object had orchestrated its invisibility to avoid scrutiny precisely when observation would have been most fruitful. Avi Loeb speculated that the disappearance might not be random, hinting at intentional positioning, a calculated passage behind 150 million kilometers of incandescent solar plasma, cloaking its activity from terrestrial eyes. This vanishing act introduced profound uncertainty into predictive models. Astronomers could no longer track the object's behavior in real time, nor confirm whether previously observed phenomena, nickel outgassing without iron, anomalous CO₂ dominance, or color transformations continued, intensified, or subsided. Observational gaps always complicate data interpretation, but for 3I Atlas, the 2-month solar obstruction represented more than a mere inconvenience. It was a blind spot during the critical phase when thermal and radiative processes would have been at their maximum. Instruments in solar orbit, like the Parker Solar Probe and the Solar and Heliospheric Observatory, SOHO, could potentially capture glimpses of the object, but their sensors were optimized for solar phenomena rather than faint interstellar travelers, making detection unlikely. Even spacecraft positioned beyond the Sun's glare, such as ESA's JUICE, faced significant constraints, using heat-shielded antennas that limited data transmission and observational capability. This period of invisibility was not merely a technical frustration, it had tactical implications. If 3I Atlas possessed any technological component, the perihelion window offered the perfect opportunity for activity invisible from Earth. Loeb and others proposed scenarios in which the object could execute velocity adjustments, deploy precursor probes, or otherwise maneuver without detection. Even small changes in speed 10 to 15 kilometers per second could alter the trajectory significantly, delivering potential payloads to Mars or other inner solar system targets. For a natural comet, such adjustments are impossible. Outgassing produces only modest thrusts insufficient to meaningfully change course. But for a designed object, the window behind the Sun would be optimal for any hidden operations, free from observational interference. Observers contemplated the implications for Earth and Mars alike. The Martian surface, equipped with the Curiosity and Perseverance rovers, offered limited observational data, but orbiting spacecraft would play a pivotal role in monitoring 3I Atlas when it returned to visibility. In the meantime, scientists and enthusiasts alike were forced to wait, suspended in uncertainty, bridging speculation with the constraints of physics. This enforced invisibility transformed the simple act of observation into a study of possibility, compelling humanity to consider scenarios previously relegated to theoretical exercises. It highlighted the interplay between chance, physics, and, perhaps, intent, and it underscored a central truth: in observing the cosmos, what is unseen can be as consequential as what is revealed. The disappearing act behind the Sun thus became a central narrative thread, amplifying suspense, raising stakes, and challenging the very frameworks through which astronomers interpret interstellar phenomena. As scientists wrestled with the temporary disappearance of 3I Atlas, a separate but equally unsettling anomaly emerged: the object's sheer mass. Calculations based on trajectory analysis, outgassing behavior, and observed luminosity suggested a nucleus at least 5 kilometers across, with a total mass estimated at 33 billion tons. For comparison, previous interstellar visitors like Oumuamua and Boris were minuscule, mere hundreds of meters to 1 kilometer in length, making 3I Atlas 3 to 5 orders of magnitude more massive. Its resistance to non-gravitational acceleration was particularly striking. Outgassing, even at rates measured by Webb and other telescopes, 129 kilograms per second of carbon dioxide, 6 kilograms per second of water, and 14 kilograms per second of carbon monoxide should have imparted measurable deviations in trajectory, yet the object followed a nearly perfect gravity-based path. This suggested an enormous mass, one far exceeding expectations for any interstellar comet observed to date. Such an object should statistically be extraordinarily rare. Surveys of interstellar space, based on known material densities and the expected size distribution of rocky and icy objects, predict that numerous smaller bodies should be detected before encountering a massive one like 3I Atlas. Yet only 2 interstellar visitors had been recorded prior, both orders of magnitude smaller. The lack of smaller objects preceding 3I Atlas strained the conventional understanding of interstellar populations. This mass discrepancy, coupled with its unlikely alignment and hyperbolic trajectory, led some scientists to consider that its arrival might not be random. If the object's path had been deliberately chosen, it could explain the improbable coincidence, suggesting that this was not simply a chance encounter, but potentially a visit from a specific, perhaps technological, interstellar source. The structural integrity of 3I Atlas added another layer to the enigma. Outgassing of this magnitude should induce rotational torques and material stress sufficient to fragment a loosely bound rubble pile. Yet the object remained coherent, resisting the disruptive forces that would typically break apart a comet of similar size. This implied either a solid, dense nucleus or an internal structure bound by forces stronger than self-gravity. Some researchers proposed that an artificial component might account for such resilience. Others speculated on natural explanations, such as unusually dense interstellar ice conglomerates, but the cumulative improbabilities continued to mount. The mass anomaly was closely tied to upcoming observational opportunities. The October 3rd Mars flyby, with orbiting spacecraft like the Mars Reconnaissance Orbiter, offered the first chance to measure the nucleus directly and separate it from surrounding dust clouds. High-resolution imaging and spectroscopy could constrain mass estimates, composition, and structural coherence, potentially confirming or refuting the unprecedented calculations. Until then, astronomers were left balancing the statistical improbability of the object's mass, trajectory, and composition against the possibility that 3I Atlas might simply represent an extreme natural outlier, a reminder of how little humanity truly understood about the diversity and history of interstellar bodies. Each observation to date, from mass to outgassing rates to alignment, compounded the tension between the ordinary and the extraordinary, forcing a reconsideration of what might be physically and technologically possible in the universe. The chemical idiosyncrasies of 3I Atlas continued to astonish researchers, revealing layers of complexity that challenged conventional cometary science. The James Webb Space Telescope, with its near-infrared spectrograph, measured the gas plume in early August and recorded an unprecedented composition: 95% carbon dioxide, 5% water, and trace amounts of carbon monoxide and carbonyl sulfide. These ratios starkly contrasted with expectations for comets, which typically originate in water-rich regions of stellar systems. The high CO₂ concentration suggested formation in an environment much colder or chemically distinct from our own solar system's outer reaches, perhaps in a molecular cloud or a distant planetary system where different elemental abundances prevailed. Such conditions could produce volatile distributions radically different from those observed in known comets, but the combination with other anomalies rendered purely natural explanations increasingly tenuous. The mystery deepened when considering the visual transformations documented by astronomers. Amateur observations during the September 7th total lunar eclipse captured 3I Atlas glowing bright green with a bluish tinge, a stark departure from its earlier reddish appearance. The green coloration, typically attributed to diatomic carbon emissions, was perplexing because prior spectroscopic data indicated severe depletion of these molecules. The forward explanation proposed a correlation with rapidly increasing cyanide emissions detected by the Very Large Telescope. Cyanide and related compounds can fluoresce green under ultraviolet light, suggesting that thermal processing or photochemical reactions induced by proximity to the Sun might drive both chemical and color transformations. This phenomenon, occurring within days, indicated highly reactive or previously dormant surface chemistry, possibly resulting from billions of years of cosmic ray exposure, interstellar dust impacts, and the near-zero temperature voids of interstellar space. These chemical peculiarities were not isolated. The nickel without iron anomaly persisted alongside the CO₂ dominance and cyanide spikes, forming a composite profile that challenged models of natural formation and evolution. Each component could, in theory, have a separate natural explanation. Nickel carbonyls forming in extreme interstellar cold, CO₂ enrichment due to formation around a carbon-rich star, cyanide spikes from solar heating. Yet their simultaneous occurrence, combined with the object's unusual trajectory, hyperbolic velocity, and enormous mass, created a pattern that was statistically improbable. Astronomers faced the difficult task of reconciling multiple layers of evidence, physical, chemical, and orbital, into a coherent narrative that obeyed known physical laws, all while recognizing that each anomaly added pressure to conventional interpretations. Infrared observations from Spherex further complicated the picture. Instead of detecting an extended coma typical of comets, the telescope recorded 3I Atlas as a compact point source, suggesting either that the surrounding material was unusually cold and non-emissive in the infrared, or that the luminous output observed in visible light came primarily from the object itself. Such observations implied unique thermal properties, a highly reflective or insulating surface, or an internal distribution of volatiles unlike any known comet. Together with the visible light anomalies, these findings painted a picture of an interstellar object that, while potentially natural, behaved in ways that seemed engineered, prompting both awe and cautious speculation about the mechanisms driving its unexpected chemistry and appearance. The visual anomalies of 3I Atlas challenged the very assumptions about how comets should appear in the inner solar system. The Hubble Space Telescope, in its highest resolution imaging on July 21st, captured a teardrop-shaped cocoon of dust surrounding the object, but with a startling peculiarity. The glow was elongated forward, pointing toward the Sun rather than trailing behind as expected. Comet tails are sculpted by solar radiation and wind, forming in the anti-solar direction as volatile gases and dust are expelled from the nucleus. The anti-tail of 3I Atlas, bright and structured, contradicted centuries of comet observations, It was as if the object were producing a forward-facing halo, defying the well-established dynamics of sublimation and solar radiation pressure. Such a morphology, observed in visible light, offered no simple natural explanation and became a focal point of both skepticism and fascination within the scientific community. Researchers Avi Loeb and Eric Keto attempted to explain the phenomenon through internal dust dynamics, proposing that pressure-driven expulsion of particles could push material ahead of the nucleus. Even so, they acknowledged the speculative nature of this hypothesis. Others suggested observational artifacts, such as tracking, smearing in Hubble images due to rapid motion against the star field, yet careful image analysis distinguished the forward glow from any such artifacts, confirming its authenticity. The forward halo was real, not a computational or instrumental anomaly. By August 27th, the Gemini South Telescope documented the emergence of a faint tail in the conventional anti-solar direction. This suggested either that the tail had developed with increased solar proximity or that changing viewing geometry had revealed a previously obscured structure, but it did nothing to diminish the significance of the forward-facing cocoon observed earlier. Further scrutiny of the Hubble images revealed intricate detail in the dust distribution. The cocoon extended approximately 3,000 kilometers from the nucleus, creating an exceptionally diffuse envelope. If the nucleus measured around 10 kilometers in diameter, as hypothesized, the density of dust at that distance would be diluted by a factor of 90,000 compared to the surface, yet remained sufficiently reflective to be detected by Hubble. This implied either an enormous quantity of fine particles or highly unusual reflectivity. Observations across multiple wavelength filters added another layer. Ultraviolet imaging revealed a more compact core, while red and infrared wavelengths showed extended structures, consistent with typical dust scattering properties. Smaller particles predominated near the nucleus, while larger grains extended outward, following a distribution that, superficially, resembled classical cometary physics, yet was complicated by the forward glow and anomalous chemical composition. Rotation and outgassing dynamics further intertwined with these visual anomalies. 3I Atlas rotated once every 16 hours, relatively slow for a small interstellar object, with surface velocities insufficient to account for particle ejection via centrifugal force alone. Calculations indicated that gas drag from sublimating carbon dioxide, moving at approximately 20 meters per second, was the primary mechanism for propelling dust outward. Given the measured outgassing rate, 129 kilograms per second of carbon dioxide, the dust production would be significant, enough to produce a conventional tail. Yet in July, Hubble observed only the forward halo and diffuse coma, no typical tail, indicating an unusual interplay between radiation pressure, particle size, and possibly electrostatic interactions with the solar magnetic field. Charged dust grains can behave differently from neutral particles, and the possibility of electrically influenced motion introduces a mechanism for forward-directed scattering, though such processes remain largely theoretical. The combination of dust morphology, rotation dynamics, and unusual chemical emissions positioned 3I Atlas as an object at the edge of known physics. The July forward glow, followed by the August anti-tail, exemplified the complexity of interpreting distant interstellar phenomena through remote observation. Each image and spectral analysis added data points to an intricate puzzle, a massive object with coherent structure, unprecedented chemical ratios, and visual characteristics that contradicted centuries of empirical knowledge. Scientists were confronted with a choice: continue attempting to force 3I Atlas into the framework of conventional cometary behavior, or accept that the universe had delivered a visitor that might require new models of formation, evolution, or even deliberate design. The trajectory of 3I Atlas added yet another layer of perplexity to an already confounding case. The object moved on a retrograde orbit, inclined roughly 175 degrees to the ecliptic plane, a course that, while extreme in conventional terms, placed it astonishingly close to the plane in which most planetary orbits reside. Unlike typical interstellar objects, which arrive from random directions in the three-dimensional expanse of space, 3I Atlas seemed almost deliberately aligned with the inner solar system's orbital architecture. Its passage within 30 million kilometers of Mars on October 3rd, combined with planned proximities to Venus and Jupiter, suggested a geometric precision rarely encountered in naturally occurring interstellar bodies. Statistical analysis by Avi Loeb and colleagues calculated that the likelihood of such an alignment occurring by chance was approximately 1 in 500, elevating the possibility of intentional trajectory design from speculative curiosity to a matter warranting serious scientific consideration. Further complicating this assessment, the object's hyperbolic orbit, with an eccentricity of 6.16, indicated that 3I Atlas was unbound by the Sun's gravity and destined to return to interstellar space. Tracing its motion backward suggested an origin within the thick disk of the Milky Way, possibly ejected from a star system 7 to 11 billion years old. The object's velocity prior to entering the solar system, approximately 58 kilometers per second relative to the Sun, matched expected speeds for thick-disk interstellar objects, yet its timing was uncanny. The arrival coincided with the activation of advanced observational infrastructure, including the Vera Rubin Observatory and Spherex. Whether coincidence or deliberate targeting, the alignment between observational capability and object arrival raised profound questions about the nature of its entry. Observers debated whether the trajectory could be purely natural, invoking selection bias and detection limitations. Interstellar objects passing far from the Sun or Earth would remain undetected due to faintness, meaning that the sample of observed visitors is inherently skewed toward those closely intersecting inner solar system orbits. While this explains part of the alignment, it does not fully account for the extraordinary coplanarity and near-perfect timing with our observational readiness. The combination of hyperbolic motion, retrograde inclination, and proximity to multiple planets suggested a level of coordination inconsistent with purely random dynamics. Moreover, the trajectory implied potential interactions with planetary bodies, each passage representing an opportunity to gather information or influence outcomes. Mars, being the closest target during the October 3rd flyby, became the focal point of observational campaigns, yet the alignment also opened the possibility, however speculative, of precursor probes or material transfer occurring undetected. Velocity adjustments on the order of 10 to 15 kilometers per second, trivial for a technologically capable object, could significantly alter the course, while natural sublimation processes would produce only fractional deviations insufficient to mimic such precision. The path of 3I Atlas thus presented a dual narrative, one that could be rationalized through extreme natural variability and statistical improbability, and another that hinted at deliberate navigation, a ghostly whisper of design threading through the cosmos. In sum, the trajectory of 3I Atlas challenged assumptions about the randomness of interstellar arrivals. Its alignment with the ecliptic plane, close planetary encounters, and precise timing with human observational capacity painted a picture that transcended ordinary celestial mechanics. Each data point intensified the tension between a natural explanation and the unsettling possibility of an interstellar visitor guided by intentionality. This orbital enigma, when combined with chemical anomalies, mass discrepancies, and visual peculiarities, framed 3I Atlas not merely as a curiosity, but as an interstellar enigma whose full implications demanded both rigorous scientific scrutiny and philosophical reflection. As October 3rd approached, the anticipation surrounding 3I Atlas reached a crescendo. The Mars Reconnaissance Orbiter, equipped with a high-resolution camera capable of imaging at 30 kilometers per pixel from 30 million kilometers away, was poised to provide humanity with the most detailed view of an interstellar object ever captured. For the first time, scientists could hope to directly measure the nucleus, separate it from surrounding dust, and determine whether the estimated 5-kilometer diameter and 3 billion-ton mass were accurate. If confirmed, such measurements would dramatically undermine natural cometary explanations, highlighting the extreme improbability of encountering such a massive, hyperbolically moving object without prior detection of thousands of smaller interstellar bodies. The observational campaign was unprecedented, combining multiple spacecraft Mars Express, ExoMars Trace Gas Orbiter, and the MRO employing cameras, spectrometers, and particle sensors to capture complementary data across a range of wavelengths. A critical aspect of the October 3rd observations was the search for precursor probes. Loeb and other researchers posited that smaller objects might precede 3I Atlas by tens of millions of kilometers, effectively invisible to Earth-based telescopes due to their diminutive size. Detecting such probes would require coordinated, high-precision scanning from multiple instruments orbiting Mars, searching for subtle anomalies or moving point sources within the orbital path. The implications were profound. Evidence of smaller objects could suggest deliberate deployment, hinting at technological design rather than natural origin. The window for observation was narrow, as the object would soon vanish behind the Sun from Earth's perspective, creating a fleeting opportunity to capture definitive measurements before a 2-month observational blackout. The scientific community prepared for multiple scenarios. If imaging confirmed a 5-kilometer nucleus with minimal non-gravitational acceleration despite intense outgassing, the natural comet hypothesis would become increasingly untenable. Conversely, if the nucleus appeared smaller or surrounded by a diffuse dust cloud, outgassing effects could account for trajectory stability, supporting a conventional explanation. However, previous infrared observations from Spherex suggested that the bulk of the emission came from the object itself, not surrounding dust, increasing the likelihood that the nucleus was indeed massive and dense. Each observation was thus a test of competing models: natural interstellar comet, ancient chemically altered relic, or a technologically advanced interstellar visitor. The anticipation extended beyond the scientific realm into philosophical territory. These observations were more than a measurement of mass or chemical composition. They represented an opportunity to challenge humanity's understanding of the cosmos. The possibility of a technological interstellar object arriving precisely when detection capabilities were sufficient to recognize it raised questions about the presence of intelligent life beyond the solar system and the methods by which such civilizations might monitor emerging technological species. Whether the data would confirm the anomalies, reveal new surprises, or ultimately fit within natural explanations, October 3rd marked a pivotal moment. Humanity stood on the cusp of witnessing either the extreme end of natural interstellar phenomena or the first tangible evidence of intelligence navigating the gulf between stars. Speculation about invisible precursor probes accompanying 3I Atlas intensified as the October 3rd flyby drew near. Loeb and colleagues theorized that the object could have deployed smaller reconnaissance craft ahead of the main body, traveling millions of kilometers in advance effectively invisible to Earth-based telescopes due to their diminutive size. Objects smaller than approximately 100 meters at Mars distance fall below detection thresholds, yet they would be fully capable of conducting a survey, capturing imagery, or transmitting data back to the primary body. Such a strategy mirrors how humans design interstellar missions. A mothership carries a suite of scout probes, releasing them sequentially to gather information on planetary targets before the main craft arrives. If 3I Atlas employed a similar tactic, any advanced technological component would be effectively operating outside the observational reach of conventional astronomy, hidden behind the veil of interplanetary distance and the glare of the sun during critical periods. The implications of precursor probes, while speculative, were taken seriously due to the object's extraordinary alignment and trajectory precision. Calculations indicated that a minor adjustment of 10 to 15 kilometers per second could significantly alter approach distances, enabling probes to intercept Mars or other inner solar system targets while remaining undetectable. The 2-month period during which 3I Atlas disappeared behind the Sun offered an ideal window for such operations. Unlike natural cometary fragments, which disperse unpredictably due to sublimation and outgassing forces, a controlled deployment would allow small craft to travel along predetermined paths with minimal deviation. Earth-based instruments, constrained by both distance and solar interference, would be blind to any such activities, creating the possibility of unseen reconnaissance or material delivery. Observational strategies incorporated this scenario into the campaign design. Mars Reconnaissance Orbiter's high-resolution imaging, combined with spectral analysis from ExoMars and Mars Express, was tasked not only with imaging the nucleus and coma of 3I Atlas, but also with scanning the surrounding space for anomalies consistent with small, independent objects. The coordination required precise timing, as the main body and any potential probes would be in motion relative to Mars, necessitating predictive modeling based on prior trajectory data. Analysts developed search grids and imaging sequences designed to maximize detection probability, even for faint point sources moving along complex orbital paths. The multi-instrument approach reflected an understanding that a single line of evidence would be insufficient. The hunt for probes demanded redundancy, corroboration, and continuous data streams to identify anomalies against the background of Mars and interplanetary space. The concept of precursor probes raised questions not only about detection but also about interpretation. If a small object were observed, distinguishing between natural fragments, outgassed material, and a deliberately deployed probe would be challenging. Researchers would need to analyze velocity, trajectory, composition, and light emission patterns to determine whether it conformed to known physical models or suggested artificial design. Even the absence of detected probes would not eliminate speculation, as craft could have been too small, optically neutral, or positioned outside the observational window. This uncertainty underscored the philosophical weight of the October flyby. Humanity would gather unprecedented data on an interstellar object, yet complete certainty might remain elusive, leaving open the possibility that 3I Atlas had operated in ways deliberately concealed from our instruments, bridging the realms of natural science and the potential for extraterrestrial engineering. Scientific debate over 3I Atlas was fierce, reflecting a broader tension between conventional astrophysics and the emerging anomalies presented by this extraordinary object. Avi Loeb's assessment of a potential technological origin faced immediate scrutiny from peers, who argued that extraordinary claims required extraordinary evidence. Critics, including Jason Wright at Penn State and other leading astronomers, labeled the comparison to industrial nickel production misleading, cautioning against motivated reasoning that could overinterpret unusual spectral data. NASA's representatives, such as Tom Statler, emphasized that 3I Atlas resembled comets in broad strokes, performing behaviors that could be explained by sublimation and solar heating. Yet, these rebuttals often skirted the core anomalies: the absence of iron accompanying nickel, the extreme CO₂-to-water ratio, and the statistically improbable trajectory, leaving an uncomfortable gap between explanation and observation. The debates extended beyond journals into online forums and professional conferences. Amateur astronomers, often dismissed for technical errors or equipment limitations, had captured images showing defined edges and compact structures beneath the gaseous envelope, challenging the notion that all anomalies could be dismissed as observational artifact. Professional astronomers occasionally engaged, citing smearing, atmospheric distortion, or chromatic aberration as causes for irregular features, yet few attempted replication with larger instruments. This polarization illustrated a broader philosophical question. When confronted with phenomena at the edge of known physics, how should science weigh anomalies against statistical and empirical norms? The divergence of opinion underscored the limits of observational coverage, the biases inherent in human interpretation, and the difficulty of reconciling extraordinary data with established theoretical frameworks. The controversy was compounded by the temporality of observation. 3I Atlas's perihelion passage and subsequent disappearance behind the Sun imposed a strict temporal constraint on data acquisition. Any conclusions drawn before or during October 3rd would remain provisional, reliant on limited imaging, spectroscopy, and predictive modeling. The high stakes of misinterpretation loomed large. Affirming a technological origin prematurely could provoke sensational claims, while dismissing anomalies outright risked overlooking evidence of profound significance. Consequently, the scientific community approached the October observations with both caution and urgency, balancing skepticism with the necessity of rigorous analysis. This tension also influenced how data was interpreted. Spectroscopic measurements, emission line analysis, and trajectory calculations became battlegrounds for competing hypotheses. Proponents of natural explanations highlighted the potential for unusual but not impossible chemical and physical processes, while advocates for technological interpretations emphasized pattern recognition, improbability, and analogies to engineered systems. Each anomaly, chemical, visual, or orbital, was examined in isolation and in aggregate, seeking coherence in a dataset that resisted simple categorization. By framing the debate in terms of probabilities, known physics, and observational fidelity, researchers sought to navigate between extremes, rejecting unfounded speculation without ignoring the extraordinary nature of 3I Atlas. The controversy around 3I Atlas exemplified the challenge of frontier science, where evidence stretches existing paradigms and demands careful negotiation between open-mindedness and methodological rigor. It highlighted not only the mysteries of the cosmos, but the philosophical and sociological dimensions of scientific inquiry. How do we interpret data at the edge of comprehension? And how do collective biases, institutional norms, and observational limitations shape our understanding of events that may redefine the boundaries of natural law? 3I Atlas thus became both a scientific and cultural phenomenon, provoking dialogue, skepticism, and wonder simultaneously, preparing the stage for a series of observations that could either reconcile anomalies or further expand the envelope of cosmic mystery. Infrared observations introduced a new dimension to the 3I Atlas enigma, challenging assumptions about its physical and thermal properties. The Spherex telescope, observing in infrared, detected the object as a concentrated point source rather than an extended, diffuse coma typical of comets at similar distances from the Sun. Comets usually emit extended infrared radiation because sublimating ices carry heat away from the nucleus, warming surrounding dust and gas that then radiates in thermal wavelengths. The absence of such an extended emission in 3I Atlas suggested either that the surrounding dust and gas were exceptionally cold, non-emissive, or that the observed radiation originated primarily from a solid, compact nucleus. This discrepancy between visible light images, which revealed extended halos and forward glows, and infrared data, which indicated concentrated emission, introduced a fundamental puzzle. How could an object appear diffuse and active in one wavelength regime, while compact and inert in another? Thermal considerations provided potential explanations but also opened new questions. If the surface were highly reflective, it might bounce incident sunlight away before significant heating could occur, preventing the expansion of an infrared-emitting coma. Alternatively, insulating materials or a rapidly spinning nucleus could distribute energy across the surface, moderating localized heating and limiting sublimation-driven thermal emission. Each scenario, while plausible, required conditions far outside those observed in any other interstellar comet or solar system object. The combination of spectral anomalies, unexpected chemical composition, and thermal behavior suggested that either extreme natural processes were at play, or that additional, possibly artificial, mechanisms influenced surface and coma characteristics. The contrast between Spherex's infrared findings and visible light observations also reinforced the need for multi-wavelength analysis. Dust particle behavior, reflective properties, and thermal inertia interact in complex ways, and only by comparing data across spectra could scientists infer a coherent model. For example, carbon dioxide sublimation detected in visible and ultraviolet spectra correlated with dust ejection velocities, yet the absence of corresponding infrared emission implied unusual thermal or radiative properties. Likewise, the forward-facing halo observed by Hubble, with particles moving at roughly 20 meters per second, persisted alongside a point-like infrared signature, suggesting a decoupling of physical dust distribution from thermal emission. These infrared anomalies had profound implications for interpreting 3I Atlas. They called into question assumptions about mass, density, and nucleus size, derived from visible light brightness alone. If much of the observed light came from reflective or highly unusual materials rather than conventional dust scattering, models estimating mass and structure could be misleading. Furthermore, the divergence between visual and infrared properties suggested processes or compositions not represented in any previously observed solar system object, reinforcing the notion that 3I Atlas occupies a category either extremely rare or unprecedented. Scientists prepared for the upcoming Mars flyby and perihelion observations with this duality in mind, understanding that infrared and visible light data together might confirm or refute existing models, potentially providing the first comprehensive characterization of an interstellar object with such complex and contradictory properties. The outgassing dynamics of 3I Atlas further defied expectations, revealing a pattern of exponential increase in volatile and metallic emissions that was inconsistent with standard cometary models. Observations from the James Webb Space Telescope and the Very Large Telescope indicated that nickel emissions, initially modest at roughly 10 circumflex 21 atoms per second in July, surged 25-fold by late August as the object moved closer to the Sun. Carbon dioxide, already dominant, continued to drive rapid dust and particle ejection, yet the resulting non-gravitational acceleration remained remarkably low. Normally, outgassing produces measurable deviations in a comet's orbit, with asymmetrical jets acting like microthrusters, pushing the nucleus off a purely gravitational path. In the case of 3I Atlas, despite substantial mass loss, the trajectory deviated by less than 15 meters per day, squared a minute fraction relative to the intensity of emissions. This implied an immense, dense nucleus capable of resisting perturbations, a property far exceeding typical interstellar visitors or solar system comets of comparable size. The chemical composition of the outgassed material also posed questions about the processes governing the nucleus. Nickel sublimation without iron, coupled with steep increases in cyanide and other carbon-based compounds, indicated surface chemistry undergoing rapid transformation under solar heating. Some theorists proposed that cosmic rays over billions of years could have altered molecular bonds in ways that produce highly unusual emission profiles. Yet the scale and coherence of the outgassing suggested more than incidental chemical evolution. It hinted at either an unprecedented natural structure or a system engineered to release specific materials in controlled quantities. The temporal correlation between proximity to the Sun and the sharp rise in emissions amplified the mystery, implying either extreme thermodynamic sensitivity or adaptive response. Dust dynamics contributed additional complexity. Particles ejected at velocities around 20 meters per second created halos and forward-facing glows inconsistent with centrifugal mechanisms, given the 16-hour rotation period of the nucleus. Radiation pressure and electrostatic effects may have acted upon micron-scale dust, redirecting particles in ways that produced the anomalous forward glow observed by Hubble. Charged dust interactions with solar magnetic fields could concentrate or disperse particles unpredictably, complicating models of tail formation and particle trajectories. These effects, combined with non-standard thermal emission in infrared, suggested a delicate interplay of forces rarely observed in natural interstellar objects, pointing to either extreme natural conditions or the influence of technology beyond current comprehension. The outgassing patterns also influenced observational planning. Rapidly evolving emissions implied that measurement windows were critical. Any delays could result in missed chemical signatures or misinterpretation of the nucleus's behavior. Multi-instrument campaigns were therefore timed to capture both peak outgassing and subsequent changes as 3I Atlas approached perihelion. Researchers understood that each data point, from metal emission rates to CO₂ flux, would be integral to modeling mass, density, and potential technological attributes. The exponential nature of the emissions underscored the urgency. The object was dynamic, unpredictable, and profoundly informative, offering insights that could redefine our understanding of interstellar bodies, planetary system formation, and the possibility of extraterrestrial engineering. Beyond the immediate anomalies of outgassing and chemical composition, the broader question of 3I Atlas's origin loomed over every analysis. Its formation environment, whether natural or artificial, could not be inferred from mass, trajectory, or emissions alone. Spectroscopic data suggested a history far removed from the solar system. Low metallicity combined with CO₂ dominance and minimal water-implied formation in a cold, chemically distinct region, possibly within the thick disk of the Milky Way. Such a birthplace, between 7 and 11 billion years ago, would predate the Sun and most planetary systems in the local stellar neighborhood. The object could be a relic of early galactic evolution, a fragment ejected from a long-dead star system, or a planetary system with unique compositional characteristics. Cosmic ray exposure, collisions with interstellar dust, and the near-zero temperatures of interstellar space over billions of years could have dramatically altered surface chemistry. producing the nickel without iron and other spectral anomalies observed. This temporal and chemical perspective opened a spectrum of interpretations. One possibility was that 3I Atlas was an ancient natural comet, its surface modified over billions of years to present properties that now defy conventional models. Extended exposure to cosmic radiation could catalyze chemical rearrangements, concentrating CO₂ and other volatiles while depleting water. Simultaneously, impacts by micrometeoroids and exposure to interstellar dust could cause localized heating or chemical processing, contributing to the observed emission spikes. The pattern of emissions, color transformations, and physical properties could, in principle, be explained by an extreme yet natural evolutionary trajectory over cosmic timescales. Alternatively, the anomalies could hint at a technological origin with a level of precision and control in emission patterns, trajectory alignment, and mass distribution beyond natural processes. The possibility of deliberate design could account for the nickel-only emissions, precise trajectory, and coherent structure of a massive nucleus. Theoretical modeling suggested that even modest adjustments in velocity or orientation, well within the capability of an advanced propulsion system, could account for the improbable alignment with the ecliptic plane and targeted planetary flybys. If such engineering were in play, the object would represent not only an interstellar visitor, but a messenger of technology, observing or interacting with the solar system in ways previously considered science fiction. Upcoming observations from the Mars Reconnaissance Orbiter and other spacecraft would be pivotal in resolving this uncertainty. High-resolution imaging, spectroscopy, and multi-angle analysis could differentiate between surface evolution consistent with extreme natural processes and patterns indicative of deliberate control or structural design. Whether the object was an ancient cosmic relic or an interstellar probe, its origin story, informed by formation environment, chemical composition, and trajectory, challenged the scientific community to reconcile observed phenomena with both known astrophysical mechanisms and the tantalizing possibility of intelligent intervention. The question of origin thus became central, framing all subsequent investigations and shaping the anticipation surrounding the October 3rd flyby and beyond. October 3rd marked a pivotal moment in humanity's engagement with 3I Atlas. The interstellar object would pass within 29 million kilometers of Mars, presenting the first opportunity for direct, high-resolution observation from orbit. The Mars Reconnaissance Orbiter, with its high-resolution imaging science experiment, HiRISE camera, was capable of distinguishing surface features at a resolution of 30 kilometers per pixel, sufficient to separate the nucleus from surrounding dust clouds and determine whether the previously estimated 5-kilometer diameter and 3 billion-ton mass were accurate. These observations promised to resolve multiple anomalies simultaneously: the structure and coherence of the nucleus, the distribution of outgassed materials, and potential asymmetries in emission that could indicate rotational or directional behavior. For planetary scientists and astronomers, the flyby represented an unprecedented opportunity to test competing hypotheses about 3I Atlas's origin, composition, and potential technological features. Complementing HiRISE, instruments aboard Mars Express and the ExoMars Tracegas Orbiter employed multi-wavelength cameras, spectrometers, and particle detectors to gather parallel datasets. While primarily designed to study the Martian surface and atmosphere, these instruments were repurposed to characterize the approaching interstellar visitor. By observing across visible, ultraviolet, and infrared spectra, scientists aim to compare emission patterns from the Martian vantage point with Earth-based and space telescope data, cross-validating chemical, thermal, and physical properties. This multi-platform approach was crucial because three I-Atlas exhibited phenomena such as the forward glow, anti-tail formation, and non-gravitationally stable trajectory that required corroboration across observational modalities to ensure accurate interpretation. A central focus of the October flyby was the search for precursor probes. Loeb and others theorized that smaller objects might have been deployed ahead of the main body, possibly reaching Mars while the parent object remained under observation. Detecting such probes required precise scanning of the surrounding interplanetary space, identifying faint point sources against the background of stars and planetary reflection. If successful, the detection of independent objects traveling along calculated trajectories would provide compelling evidence for intentional deployment, transforming the interpretation of three I-Atlas from a natural anomaly to a potential engineered system. The orbital dynamics of the probes, combined with their relative positions to Mars, could indicate deliberate targeting or data collection, offering unprecedented insight into interstellar engineering strategies. The stakes of the flyby were heightened by the impending disappearance of three I-Atlas behind the Sun for 2 months at Perihelion. Observations conducted on October 3rd would constitute the only near-term opportunity to gather comprehensive data before a period of observational blackout. Any gaps in measurement could obscure critical phenomena, including potential trajectory adjustments, fragmentation, or precursor probe activity. Consequently, scientists meticulously calibrated instruments, optimized imaging schedules, and coordinated between orbiting spacecraft to maximize temporal coverage and minimize the risk of missing transient or subtle features. The October 3rd encounter represented a decisive juncture. It was a rare convergence of observational capability, object proximity, and scientific anticipation, offering a chance to resolve long-standing questions while leaving open the tantalizing possibility of entirely new discoveries. The search for precursor probes during the October 3rd flyby added a layer of strategic complexity to the observational campaign. Scientists had to anticipate that three I-Atlas might have deployed smaller objects, traveling tens of millions of kilometers ahead of the main body, effectively invisible to Earth-based telescopes due to their size, likely below 100 meters. These hypothetical probes, if present, would be capable of approaching Mars undetected, performing reconnaissance or data collection before the main object arrived. To detect them, the Mars Reconnaissance Orbiter, in coordination with Mars Express and the ExoMars Trace Gas Orbiter, executed precise scanning protocols covering predicted orbital paths with repeated imaging across multiple wavelengths. Analysts created predictive grids based on prior trajectory calculations, factoring in potential deviations caused by solar radiation pressure, gravitational influences, and outgassing effects from the main body. Every image was scrutinized for point-like sources that could indicate the presence of a deliberate technological deployment, distinguishing them from cosmic debris or instrumental artifacts. The implications of detecting precursor probes were profound. If independent objects were confirmed, their presence would suggest intentional design, transforming three I-Atlas from an anomalous interstellar object into a coordinated system potentially engineered to interact with planets in the inner solar system. Such findings would challenge fundamental assumptions about interstellar visitation, providing the first evidence of complex interstellar technology operating beyond the detection range of conventional instruments. Conversely, the absence of observed probes would not conclusively dismiss the hypothesis. Objects could be smaller than detection limits, optically neutral, or positioned outside the observation window. Therefore, the search required both rigor and patience, acknowledging the inherent limitations of remote sensing, while preparing to interpret any anomalies with careful statistical and physical analysis. The planning for this search also reflected the temporal constraints imposed by the object's trajectory. After October 3rd, 3I Atlas would approach perihelion and disappear behind the Sun for 2 months, eliminating the possibility of immediate follow-up from Earth-based or Mars-orbiting instruments. This narrow observation window elevated the importance of preemptive planning and the coordination of multiple spacecraft, ensuring coverage of as many potential probe paths as possible. Analysts accounted for velocity vectors, predicted gravitational interactions, and the potential for propulsion-assisted maneuvers, modeling a range of plausible scenarios for probe behavior. The endeavor represented a unique convergence of astrophysics, orbital mechanics, and observational strategy, emphasizing the challenge of detecting small, fast-moving objects at extreme distances. Ultimately, the precursor probe search underscored a central tension in the study of 3I Atlas: the need to reconcile the extraordinary with the unobservable. Every image, every data point, became a critical piece of a puzzle that might reveal natural extremes, technological artifacts, or phenomena beyond current scientific understanding. The coordinated Mars flyby offered the best chance to detect subtle anomalies or independent objects, and the results would inform interpretation of subsequent perihelion behavior, potential fragmentation events, and chemical evolution. In this high-stakes context, the scientific community was acutely aware that the outcome of October 3rd could either resolve long-standing questions or propel humanity further into uncertainty, deepening the enigma of 3I Atlas and its place in the cosmos. The statistical improbability of 3I Atlas's characteristics added a psychological and intellectual weight to its study. The object was massive, with a nucleus estimated at 5 kilometers in diameter, and yet it exhibited hyperbolic motion, traveling at 137,000 miles per hour relative to the Sunday. Its trajectory was nearly perfectly aligned with the ecliptic plane, threading past Mars, Venus, and Jupiter, an arrangement calculated to occur naturally in only 1 out of 500 cases. To compound the anomaly, the object exhibited extreme chemical and physical behavior: nickel sublimating without iron, a CO₂-dominated volatile profile, rapid color shifts, and unusual dust dynamics, including a forward-facing glow pointing toward the Sunday. Each feature, taken individually, might stretch the bounds of expectation but remain within the realm of possibility. Taken together, however, they formed a constellation of improbabilities that defied conventional probabilistic reasoning and demanded careful evaluation. Astronomers began quantifying the odds, integrating models of interstellar object populations, orbital dynamics, and chemical formation processes. Known distributions of interstellar comets suggested that smaller bodies should vastly outnumber large ones, yet 3I Atlas arrived before any intermediate-sized object had been catalogued, creating a detection bias that was statistically extreme. The probability of encountering such a massive object on a nearly perfect trajectory, coinciding with the emergence of advanced observational capability, suggested either an extraordinary natural fluke or an unseen mechanism of orchestration. This calculation did not prove artificiality, but highlighted the tension between random chance and the pattern of observations, forcing scientists to confront the limits of inference in cases at the extreme margins of experience. The improbability extended beyond trajectory and mass. Temporal coincidence played a role. 3I Atlas arrived precisely when the James Webb Space Telescope, Hubble, and other instruments were capable of capturing detailed spectra and images. Observational windows for interstellar objects are typically limited. Most pass undetected, either too faint or arriving when instruments are not aligned. The object's appearance during a period of heightened observational readiness amplified both its scientific and philosophical significance. It created an almost surreal alignment of cosmic chance and human capability, framing the encounter as an extraordinary opportunity to test theoretical models, explore chemical anomalies, and potentially detect technological signatures, all within a narrow time frame. The statistical landscape informed both interpretation and debate. Natural explanations required, invoking extreme but physically plausible scenarios, formation in an unusual stellar environment, millennia of interstellar processing, and rare alignment by chance. Technological hypotheses, in contrast, gained credibility precisely because the confluence of mass, trajectory, chemical composition, and temporal coincidence stretched natural explanations to their limits. Scientists faced a dual challenge: remain anchored in empirically grounded physics while remaining open to phenomena that might lie beyond conventional understanding. The improbability of 3I Atlas thus became not only a quantitative assessment but a philosophical prompt, urging the community to consider both the limits of chance and the possibility that the universe might produce or deliver objects that challenge the very assumptions of natural law. Historical context offered valuable perspective on 3I Atlas, situating it among the few interstellar visitors humanity had ever observed. Oumuamua, detected in 2017, and Borisov, discovered in 2019, provided precedent, but both were markedly different in scale, composition, and behavior. Oumuamua, roughly 200 meters in length, displayed a peculiar elongated shape and non-gravitational acceleration without a visible coma, sparking debates over its natural versus artificial origin. Borisov, by contrast, resembled a conventional comet rich in water and carbon monoxide, following a hyperbolic trajectory with moderate outgassing effects. Compared to these objects, 3I Atlas was a behemoth, both in mass and chemical complexity, defying the expectations established by its predecessors. Its nickel emissions, CO₂ dominance, and forward-directed dust halo presented a profile unmatched in the observational record, forcing astronomers to reconsider assumptions based on the limited sample of prior interstellar encounters. The comparison highlighted the exceptional nature of 3I Atlas. Unlike Oumuamua and Borisov, which could plausibly be accommodated within models of interstellar object ejection from young planetary systems, 3I Atlas challenged those models at multiple levels. Its massive size, improbable trajectory alignment, and complex chemical behavior extended beyond the statistical envelope predicted for interstellar populations. While Oumuamua's non-gravitational motion could be attributed to outgassing or radiation pressure, the low deviation in 3I Atlas's trajectory, despite extreme outgassing, required either an extraordinarily dense nucleus or a control mechanism, raising the specter of deliberate guidance. The combination of historical precedent and deviation provided a framework to assess anomaly. Oumuamua and Borisov illustrated the natural variance of interstellar objects, while 3I Atlas occupied a position on the extreme tail of probability, testing the limits of these models. Historical precedent also informed observational strategies. Lessons learned from Oumuamua's rapid fading and Borisov's trajectory highlighted the importance of timely detection, multi-wavelength monitoring, and coordination across observatories. Unlike the smaller, faster-moving Oumuamua, 3I Atlas's massive size and slower relative motion permitted extended observation, yet its perihelion passage and solar obscuration imposed critical temporal constraints. Observers applied these lessons to the October 3rd Mars flyby, employing predictive modeling, multi-platform imaging, and spectroscopy to capture as much data as possible within the narrow window, seeking evidence that could either align with natural expectations or support the more extraordinary technological hypothesis. Ultimately, placing 3I Atlas in historical context underscored both continuity and divergence. It was part of a lineage of interstellar visitors, yet it represented a profound outlier in mass, chemical composition, trajectory, and visual morphology. This juxtaposition sharpened the scientific lens. Patterns and anomalies could now be evaluated with reference to prior interstellar objects, emphasizing how 3I Atlas simultaneously fit and broke existing paradigms. By situating the object historically, astronomers were able to frame questions with greater precision, teasing apart phenomena that were extreme but explainable from those that might hint at processes natural or engineered beyond current understanding. In this way, historical context did not diminish the mystery, it amplified it, providing a comparative baseline that made the extraordinary nature of 3I Atlas all the more apparent. The orbital analysis of 3I Atlas revealed further layers of complexity, illustrating a hyperbolic trajectory that defied simple classification. With an eccentricity of 6.16, the object was clearly unbound to the Sun, destined to exit the solar system after its inner passages. Yet the alignment of its path with the ecliptic plane, intersecting the orbits of Mars, Venus, and ultimately Jupiter, suggested a near improbable precision. Unlike the randomized angles typically associated with interstellar objects, 3I Atlas's motion exhibited a coherence that was difficult to reconcile with purely natural mechanisms. Scientists calculated that the probability of a random interstellar body traversing such a path coinciding with planetary alignments was exceedingly low, elevating considerations of design, intentionality, or rare cosmic coincidence. Velocity measurements reinforced the exceptional nature of the orbit. Traveling at approximately 58 kilometers per second relative to the Sun, 3I Atlas possessed sufficient kinetic energy to escape gravitational capture, yet its approach minimized solar perturbation, preserving a near-perfect hyperbolic trajectory. Outgassing effects, typically responsible for minor accelerations in cometary motion, failed to significantly alter its course, implying a nucleus of immense mass and density capable of resisting non-gravitational forces. The combination of hyperbolic velocity, orbital inclination, and minimal trajectory deviation suggested a level of physical coherence previously unobserved in interstellar objects. Analysis of timing further intensified the anomaly. 3I Atlas arrived during a period of unprecedented observational capability, with Webb, Hubble, Spherex, and Mars orbiters simultaneously available to capture multi-wavelength data. The synchronization between its arrival and humanity's capacity for detection magnified the philosophical and scientific weight of the event. Whether coincidence or deliberate alignment, the timing allowed for comprehensive observation of chemical emissions, dust morphology, and potential precursor probes during the narrow perihelion window. The orbit was not merely a path through space. It framed the narrative of observation, dictating when and how scientists could collect data essential for interpreting the object's nature. This hyperbolic orbit also provided opportunities to anticipate future interactions. The March 2026 close approach to Jupiter offered a unique chance to observe gravitational effects on trajectory, rotational dynamics, and potential material shedding. Simulations suggested that tidal forces from Jupiter could induce subtle rotational variations or surface stresses, allowing researchers to probe structural integrity and nucleus composition indirectly. The orbit's configuration thus functioned as a natural experiment, enabling tests of hypotheses concerning mass, cohesion, and emission mechanisms that could not be otherwise performed. In sum, the trajectory of 3I Atlas, hyperbolic, precisely aligned and minimally perturbed, reinforced the object's anomalous nature, providing both a logistical framework for observation and a profound stimulus for scientific inquiry into its origin, composition, and potential technological implications. Timing became a critical factor in interpreting 3I Atlas, adding both urgency and philosophical weight to the observational campaign. Its approach coincided with humanity's most advanced suite of instruments ever assembled, including the James Webb Space Telescope, Hubble, Spherex, and Mars-orbiting assets such as MRO, Mars Express, and ExoMars. Had 3I Atlas arrived even a decade earlier, many of its chemical, visual, and physical anomalies might have gone undetected. This temporal coincidence elevated the encounter from a routine observation to a unique event, creating a near-perfect window to study the most extreme interstellar object ever recorded. The timing underscored the serendipity, or perhaps the design implicit in the event, raising questions about the universe's capacity to orchestrate phenomena precisely when humanity is equipped to perceive them. The temporal alignment also constrained scientific methodology. Data acquisition had to occur within a narrow window prior to perihelion, after which the object would vanish behind the Sun for roughly 2 months. The opportunity to capture high-resolution images, spectroscopic data, and potential precursor probes was therefore fleeting. Observational campaigns were meticulously scheduled, coordinating multiple instruments to maximize coverage and minimize observational gaps. Scientists modeled predicted emissions, rotational states, and potential outgassing patterns to optimize timing, ensuring that each instrument would capture the most informative snapshots of the object's behavior. Failure to acquire data during this interval could result in missed anomalies, incomplete chemical characterization, or failure to detect technological signatures, leaving uncertainties unresolved for years. This temporal coincidence had broader philosophical implications as well. The alignment of object arrival and observational readiness suggested either extraordinary cosmic luck or, in the most speculative scenarios, deliberate timing. In contemplating such possibilities, researchers were forced to consider both the rarity of interstellar encounters and the mechanisms by which intelligent interstellar actors could monitor or interact with emergent civilizations. While no definitive evidence of artificiality existed at this point, the coincidence prompted reflection on the relationship between chance, observation, and understanding in the universe. The fleeting window highlighted the delicate balance of opportunity and limitation inherent in astrophysical observation. The universe revealed its secrets only when conditions allowed, and human understanding was constrained by both temporal and technological factors. Finally, the timing reinforced the urgency for interpretation. Each observation, from chemical anomalies to trajectory deviations, would be critically assessed, cross-referenced, and modeled to build coherent theories regarding 3I Atlas's origin, behavior, and potential implications. The intersection of timing, mass, trajectory, and chemical uniqueness framed a scenario in which both natural and technological explanations had to be rigorously evaluated. The October 3rd window thus served not only as a practical observational opportunity, but also as a lens through which the broader mysteries of the cosmos could be contemplated, merging the empirical with the philosophical in the pursuit of understanding a visitor from the stars. Looking beyond Mars, the scientific community set its sights on the next major interaction, the close approach to Jupiter in March 2026. This encounter promised to provide an unprecedented natural experiment, allowing researchers to observe how 3I Atlas would respond to intense gravitational forces and the planet's powerful magnetosphere. Tidal interactions could subtly influence rotation, surface stress, or even fragment loosely bound surface layers, revealing critical information about the object's internal cohesion and structural integrity. Unlike the Mars flyby, which primarily provided observational data on nucleus size, chemical composition, and potential precursor probes, the Jupiter encounter offered the opportunity to examine dynamic responses in situ, testing theories about material strength, internal density, and potential engineered features. Trajectory modeling indicated that gravitational perturbations from Jupiter could slightly adjust 3I Atlas's hyperbolic path, potentially inducing measurable changes in orientation or velocity. These perturbations were expected to be small but detectable, serving as natural probes of the object's mass distribution and structural characteristics. By analyzing post-encounter trajectory adjustments, astronomers could infer internal mass concentration, rotational inertia, and whether the object possessed characteristics inconsistent with natural formation. Such indirect measurements were crucial given the observational limits imposed by distance and solar glare, allowing researchers to leverage planetary physics as a tool for remote structural analysis. Multi-wavelength observation plans were prepared for the Jupiter encounter. Earth-based telescopes would complement spacecraft observations, capturing high-resolution imaging, spectral analysis, and photometric monitoring. Observers anticipated the continuation of unusual chemical emissions, including nickel, carbon dioxide, and cyanide, and sought to determine whether emission rates or surface characteristics would shift under Jupiter's tidal stress. The object's interaction with the magnetosphere was also of interest. Charged dust particles could respond to magnetic fields, potentially altering tail morphology or producing novel particle distributions, further informing models of outgassing dynamics and dust physics. The Jupiter flyby also carried philosophical and scientific implications. If 3I Atlas demonstrated structural resilience under tidal forces inconsistent with natural cohesion, it would reinforce the hypothesis that the object possessed unusual material properties, potentially engineered or otherwise beyond known astrophysical processes. Alternatively, natural explanations could invoke extreme density, unusual mineralogy, or cosmic age-related transformations, providing insight into the diversity of interstellar object formation. Regardless of the outcome, the encounter exemplified how celestial mechanics could serve as an investigative tool, enabling the study of interstellar objects at scales and precision impossible through passive observation alone. The March 2026 flyby thus represented both an empirical opportunity and a continuation of the philosophical inquiry initiated by 3I Atlas, the intersection of probability, physics, and the limits of human understanding in the face of an extraordinary cosmic visitor. Sequential observations of 3I Atlas revealed chemical patterns that deepened the mystery, hinting at processes both complex and possibly deliberate. As the object traversed the inner solar system, emission rates of nickel, carbon dioxide, cyanide, and other volatiles fluctuated in ways that defied simple thermal models. For example, CO₂ release increased disproportionately compared to insolation, while nickel sublimation surged exponentially as the object approached perihelion. Cyanide, absent in early July observations, appeared suddenly in August, coinciding with the dramatic color change from deep red to emerald green. The correlation between chemical shifts, surface emissions, and spectral color changes suggested either a highly reactive and chemically heterogeneous surface or a mechanism for controlled release, prompting speculation that 3I Atlas might be performing functions analogous to engineered activity. Patterns of emission over time also revealed a degree of regularity, raising questions about rotational dynamics and surface heterogeneity. The object rotated once every 16 hours, allowing thermal cycling and differential illumination across its surface. Some peaks in chemical release coincided with areas facing the Sun, but not all. Certain emissions occurred from regions predicted to be in shadow, suggesting either subsurface reservoirs activated by internal processes or unusual solar penetration effects. The forward-directed dust cocoon and antitail, observed consistently over multiple weeks, implied that the distribution of ejected particles was influenced not solely by rotation or solar wind, but possibly by underlying structural or energetic processes capable of directing material in controlled patterns. These sequential patterns were crucial for evaluating hypotheses of origin. A natural explanation might posit that the object's surface had been chemically modified over billions of years in interstellar space, resulting in extreme heterogeneity and highly reactive zones. Cosmic rays, micrometeoroid bombardment, and temperature cycling could have created areas of differential sublimation, explaining some irregularities. However, the precision, timing, and correlation with color shifts challenged purely natural interpretations. If a technological mechanism were involved, the observed emission patterns could represent an engineered control of material release, rotational stabilization, or environmental sensing. The regularity of the anomalies, coupled with the improbability of chance alignment with observational windows, lent credence to this more speculative interpretation. In preparation for upcoming observation windows, scientists constructed models incorporating these temporal chemical patterns. They simulated rotational states, sublimation dynamics, and particle trajectories to predict future emissions and optimize telescope targeting. Understanding these patterns was essential for interpreting both perihelion activity and potential precursor probes, as emissions could influence detectability and tail morphology. The chemical sequence became a narrative of its own, a story told not in words but in spectral lines, dust behavior, and dynamic interactions with solar radiation. Each successive observation built upon the last, revealing a complexity that blurred the line between natural extremity and deliberate engineering, and deepened the collective awareness of how little was truly known about interstellar objects capable of such extraordinary behavior. The behavior of 3I Atlas's dust offered a window into forces acting at scales both subtle and extraordinary. Unlike ordinary comets, whose dust particles follow predictable paths shaped primarily by radiation pressure and gravity, 3I Atlas exhibited complex dynamics that suggested multiple interacting influences. Fine particles, ejected at roughly 20 meters per second, formed an extended halo visible in visible light observations, while the forward-facing dust cocoon persisted against expectations, pointing sunward rather than trailing behind the nucleus. Electrostatic interactions, driven by charged dust grains responding to the Sun's magnetic field, provided a plausible mechanism for this deviation. Micron-scale particles could acquire electric charge through photoionization, then experience Lorentz forces that redirected them relative to neutral grains. Such effects, while negligible for larger debris, become significant for finely dispersed material, offering a partial explanation for the unusual morphology observed. Radiation pressure remained a primary driver, yet its influence interacted non-linearly with particle size and charge. Larger grains behaved predictably, forming an anti-solar tail, while smaller, charged particles displayed complex motion, sometimes even reversing trajectory relative to the Sunday. The juxtaposition of forward and backward-directed dust indicated a sophisticated interplay of forces, reflecting both the intrinsic properties of particles and the environment of the inner solar system. Thermal gradients, sublimation jets, and rotational forces combined to create dynamic, time-dependent structures, producing the luminous halos and color transitions that had captivated both professional and amateur observers. This multiplicity of factors challenged the adequacy of conventional models, necessitating multi-scale simulations that accounted for electromagnetic, gravitational, radiative, and thermodynamic effects simultaneously. The dust dynamics also provided indirect insights into the nucleus. The sustained coherence of the forward halo suggested a continuous, regulated source of particle emission rather than episodic or random outbursts. This could imply subsurface reservoirs of volatiles selectively activated by thermal or internal processes, or, in the most speculative interpretation, mechanisms guiding particle ejection deliberately. The consistency of particle velocities, distribution angles, and spectral properties over weeks reinforced the impression of structural integrity, massive cohesion, and a nucleus capable of maintaining coordinated outflows despite intense solar heating. Observations from multiple instruments allowed scientists to map particle behavior across wavelengths, revealing correlations between visible light scattering, ultraviolet fluorescence, and infrared thermal emission, providing a multidimensional understanding of the dust environment. Dust behavior had further implications for observational strategy. The forward halo and anti-tail influenced brightness measurements, spectral analysis, and trajectory interpretation, without accounting for the complex interplay of charged particles, thermal effects, and sublimation. Mass estimates and chemical models could be skewed, leading to under- or overestimation of the nucleus's size, density, and composition. Recognizing these interactions, scientists refined predictive models, optimized observation timing, and adjusted imaging techniques to maximize information retrieval. Dust dynamics, therefore, were not merely aesthetic anomalies. They were critical indicators of underlying processes, bridging chemical emissions, rotational behavior, and structural properties. In studying 3I Atlas, dust became a messenger, revealing hidden mechanics, guiding observational decisions, and deepening the scientific narrative of an interstellar visitor whose complexity challenged comprehension at every level. The question of 3I Atlas's origin remained central. Was it a product of natural cosmic processes, or did it bear the hallmarks of engineering? The chemical, visual, and dynamic anomalies had already pushed the object beyond conventional classification. On one hand, formation in an unusual stellar environment, billions of years of cosmic ray exposure, and rare chemical evolution could potentially account for CO₂ dominance, nickel without iron, and episodic cyanide production. Theoretical models suggested that extreme conditions in distant molecular clouds or around carbon-rich stars could produce objects with highly unusual compositions and physical properties. Over billions of years, collisions with interstellar dust, thermal cycling in near-absolute zero environments, and cosmic irradiation could alter the surface chemistry and structural cohesion, creating phenomena that, while extraordinary, remained within the realm of natural processes. On the other hand, several features resisted plausible natural explanations. The forward-pointing dust halo, exponential metal emission, near-perfect ecliptic alignment, hyperbolic velocity, and enormous mass all suggested coherence and control exceeding expected cosmic variance. If one entertained the hypothesis of technology, these characteristics could indicate intentional design, materials engineered to survive interstellar travel, emission patterns programmed for specific observational or environmental effects, and a trajectory optimized for planetary flybys or reconnaissance. In this scenario, 3I Atlas was not merely a passive traveler but an active system, potentially capable of deploying precursor probes or interacting with planetary environments in subtle, undetectable ways. Analytical efforts focused on discriminating between these two extremes. Observational campaigns incorporated models of sublimation-driven dynamics, dust interactions, and rotational behavior, comparing them to patterns expected from engineered mechanisms. Multi-wavelength imaging allowed for cross-correlation between chemical emissions, dust scattering, and thermal properties, highlighting inconsistencies that natural models struggled to reproduce. Researchers examined every anomaly: color shifts, trajectory stability, mass distribution, forward halo geometry, and outgassing dynamics, assessing whether stochastic natural processes could plausibly produce the observed phenomena, or if deliberate orchestration was a more parsimonious explanation. This duality framed the scientific narrative, compelling both humility and imagination. Natural explanations required invoking extremes rarely encountered in the solar system, stretching empirical data to its boundaries. Technological interpretations required speculation about capabilities and design principles far beyond current human experience, yet offered coherent explanations for the object's suite of anomalies. Observational opportunities, particularly the October 3 Mars flyby and the March 2026 Jupiter encounter, were positioned as critical tests. Each measurement, each spectral analysis, had the potential to clarify the origin question. The study of 3I Atlas thus became not only a pursuit of understanding interstellar chemistry and physics, but also an exercise in evaluating the limits of inference, the plausibility of intelligent design, and the interpretive frameworks that shape how humanity engages with unprecedented cosmic phenomena. The contrast between professional and amateur observations of 3I Atlas highlighted the complexities inherent in studying an object of such unprecedented characteristics. Professional telescopes, Hubble, Webb, and the Very Large Telescope provided high-resolution imagery, precise spectroscopic data, and multi-wavelength analysis, but were constrained by scheduling, narrow fields of view, and the necessity of adhering to strict observational protocols. Their instruments captured detailed chemical signatures and dust morphology, yet missed broader patterns detectable only by persistent monitoring. In contrast, amateur astronomers, distributed globally and unconstrained by institutional scheduling, produced continuous imaging sequences capturing color shifts, transient features, and unexpected luminosity fluctuations. These contributions, though often scrutinized for instrumental and methodological limitations, proved invaluable, particularly in tracking temporal changes and providing context for professional datasets. The interplay between professional and amateur data created a more complete understanding of 3I Atlas's behavior. For instance, the sudden shift from red to green, first reported by amateur observers during the September 7 lunar eclipse, prompted professional teams to revisit spectral data and identify corresponding cyanide emissions. Similarly, the detection of subtle forward-directed halos by amateurs led to targeted high-resolution imaging campaigns, confirming the phenomenon with instruments like HiRISE on MRO. The synergy demonstrated the importance of integrating multiple perspectives, combining rigorous quantitative measurements with flexible, responsive observational strategies. It also highlighted the democratization of astronomy. When extraordinary objects appear, the global network of observers can capture fleeting, transient phenomena that might otherwise go unnoticed. This dynamic raised questions about observational reliability, data weighting, and interpretation. Professional astronomers applied statistical modeling to account for potential errors, atmospheric distortion, and instrument artifacts, while amateur data underwent validation through cross-correlation with independent datasets. The combined approach revealed both consistencies and anomalies, allowing researchers to discriminate between instrumental noise and genuine features of 3A Atlas. It also emphasized the iterative nature of science. Observation informs hypothesis, hypothesis guides further observation, and anomalies challenge both frameworks, fostering refinement and adaptation in near real time. Ultimately, the contrast underscored a broader philosophical point. The study of 3I Atlas required flexibility, humility, and openness to multiple perspectives. No single instrument, professional or amateur, could capture the object's full complexity. By embracing diverse sources, scientists could approach the object as a multifaceted phenomenon, integrating chemical, visual, thermal, and dynamical data into a coherent but still incomplete understanding. This collaborative observational paradigm became a model for future interstellar encounters, emphasizing that extraordinary cosmic phenomena demand extraordinary approaches where expertise, ingenuity, and global participation converge to illuminate the unknown. The tools and strategies employed to study 380 Atlas were themselves unprecedented in scope and sophistication, reflecting the challenges posed by an object that defied conventional categorization. Earth-based observatories, including Hubble and the Very Large Telescope, provided high-resolution optical and near-infrared imaging, enabling precise chemical analysis, photometry, and morphological assessment. Webb, with its unparalleled sensitivity in the mid-infrared, captured emission spectra, revealing the dominance of CO₂, the presence of nickel without iron, and subtle cyanide signals, correlating with observed color changes. These instruments, operating in concert, allowed scientists to construct multi-dimensional models of the object's behavior, integrating chemical composition, thermal properties, and dust dynamics into predictive frameworks. Complementing space-based observation, Mars-orbiting platforms such as MRO, Mars Express, and ExoMars Trace Gas Orbiter played a pivotal role in capturing high-resolution images and spectroscopy from a closer vantage point. HiRISE on MRO, with its 30 km per pixel resolution at 30 million kilometers, was capable of distinguishing the nucleus from surrounding dust and capturing detailed surface features. Multi-wavelength spectroscopy allowed for cross-validation of chemical signatures detected from Earth, while photometric analysis provided estimates of albedo, rotational state, and potential structural heterogeneity. Coordinated observations ensured that data from different instruments could be reconciled, providing a more comprehensive understanding of the object than any single observatory could achieve alone. Particle detection and dynamical modeling further expanded the analytical toolkit. Observers tracked dust grains' velocities, sizes, and spatial distribution, analyzing electrostatic and radiative forces acting on the particles. Rotational dynamics, outgassing rates, and trajectory stability were modeled to infer mass distribution, internal cohesion, and potential artificial mechanisms for material ejection. These tools allowed researchers to predict morphological changes, anticipate spectral variations, and plan observation sequences to maximize information gain. Simulations incorporated both stochastic natural processes and hypothetical engineered interventions, enabling comparative analysis between extreme natural models and technological hypotheses. The integration of these diverse tools highlighted the interdisciplinary nature of the 3I Atlas study. Observations drew upon astrophysics, planetary science, chemistry, electromagnetic theory, and computational modeling, blending empirical measurement with theoretical interpretation. Each instrument and dataset contributed unique insight, yet only through synthesis could coherent conclusions emerge. This multi-layered approach exemplified the scientific method at the frontier, where conventional assumptions are challenged and observational creativity is essential. By leveraging cutting-edge tools, scientists aimed not only to characterize 3I Atlas, but to test the boundaries of what is knowable about interstellar objects, preparing to confront questions that span from chemical evolution to the possibility of intelligent design. The broader implications of 3I Atlas extended far beyond its chemical and physical anomalies, prompting philosophical reflection on humanity's place in the cosmos. Encountering an interstellar object with such extraordinary characteristics challenged assumptions about the distribution of matter, the frequency of interstellar visitors, and the potential for intelligence elsewhere in the galaxy. If 3I Atlas were entirely natural, its existence suggested that the universe harbors objects far more complex, massive, and chemically diverse than previously believed, implying a hidden richness in the interstellar medium and a potential re-evaluation of models of stellar and planetary formation. Each anomaly, the forward-facing dust, halo, nickel emissions, hyperbolic trajectory, and improbable alignment, would then serve as a window into natural processes operating at extreme scales, revealing the subtle interplay of physics, chemistry, and cosmic history. Conversely, if the object bore technological or engineered characteristics, the philosophical stakes were magnified. An intentionally guided interstellar object, deploying precursor probes or exhibiting controlled outgassing patterns, implied intelligence capable of spanning the vast distances between stars. The temporal coincidence of its arrival with humanity's observational capabilities further accentuated the sense of cosmic significance, suggesting that advanced civilizations might monitor, interact with, or observe emergent technological species in ways that challenge conventional assumptions about contact and observation. The possibility of engineering at interstellar scales invited reflection on the limits of human understanding, the potential ubiquity of intelligent life, and the nature of technological signatures in a universe that remains largely unobserved at fine scales. These considerations extended into the temporal dimension. 3I Atlas had traveled billions of kilometers over millions of years, preserving chemical and structural information from its origin while revealing behavior shaped by interstellar processes or deliberate design. Its passage through the solar system represented a fleeting intersection between cosmic and human timeframes, a moment when ancient processes or distant intelligence became observable within the constraints of human perception. This convergence highlighted the delicate balance of chance, causality, and observation in cosmic events, emphasizing how the interpretation of interstellar phenomena depends not only on measurement but on timing, context, and perspective. Ultimately, the encounter with 3I Atlas served as a mirror for humanity's understanding of the universe. It prompted reflection on the limits of knowledge, the boundaries between natural and artificial, and the capacity of science to interpret phenomena that challenge conventional frameworks. Regardless of whether the object was natural, engineered, or somewhere in between, its study fostered a sense of humility, wonder, and philosophical inquiry, reinforcing the profound significance of interstellar observation. Each emission, trajectory, calculation, and dust particle became not just data, but a lens through which to contemplate the vastness, complexity, and potential intelligence embedded in the cosmos, urging a re-evaluation of what it means to observe and understand the universe from our small vantage point on a pale blue planet. As the October 3rd flyby and the upcoming perihelion passage unfolded, scientists contemplated multiple potential scenarios for 3I Atlas, each with implications for observation, interpretation, and cosmic understanding. One scenario envisioned the object behaving purely as a natural interstellar relic, an ancient, chemically unusual comet whose surface had evolved under billions of years of cosmic radiation, collisions, and thermal cycling. In this case, the unusual chemical emissions, color shifts, and dust morphology were extreme expressions of natural processes, representing rare but physically plausible outcomes within the diversity of interstellar bodies. Observational focus would then aim to quantify extremity, test chemical evolution models, and understand the limits of natural processes under prolonged interstellar exposure. A second scenario considered the object as a technologically engineered system, potentially deploying precursor probes, managing outgassing patterns, and maintaining structural integrity far exceeding that of a natural body. In this case, the observed anomalies nickel without iron, CO₂-dominated volatiles, forward-facing halos, and improbable trajectory alignment could be interpreted as deliberate design features. Researchers anticipated that detailed imaging from MRO and spectroscopy from Mars orbiters might reveal signs of subsurface compartments, reflective coatings, or structural patterns inconsistent with natural geology. The detection of precursor probes would constitute strong evidence of intelligent intervention, transforming the encounter from a study of natural extremity to a first observation of interstellar engineering. A hybrid scenario was also contemplated, in which 3I Atlas represented a natural object modified or augmented by intelligent intervention. For example, an ancient comet could have been retrofitted with materials or mechanisms to survive interstellar travel or to deploy probes at critical intervals. In this scenario, the chemical, visual, and dynamical anomalies were the result of both natural and artificial processes interacting over vast timescales. Observers would need to disentangle intrinsic properties from engineered features, evaluating whether emission patterns, trajectory coherence, or dust dynamics aligned with stochastic natural behavior or intentional design. Finally, the philosophical implications of each scenario influenced the interpretation of data. Natural explanations emphasized the extremity and diversity of interstellar physics, encouraging revision of models for chemical evolution, dust dynamics, and mass distribution. Technological hypotheses suggested that the universe might harbor intelligence capable of operating on interstellar scales, observing or interacting with emerging civilizations in subtle ways. The hybrid scenario merged these considerations, challenging observers to reconcile the interplay between natural evolution and intelligent influence. Each scenario framed the expectations for upcoming observations, guiding instrument targeting, temporal sequencing, and analytical focus, while maintaining an openness to surprises that might redefine humanity's understanding of interstellar phenomena and cosmic possibility. As the observational campaign reached its climax, the emotional and philosophical weight of 3I Atlas became apparent. The object, a massive, chemically and dynamically anomalous interstellar traveler, confronted humanity with questions that extended beyond astrophysics into the nature of intelligence, chance, and cosmic design. Every spectral line, every dust particle, and every trajectory calculation was both data and narrative, a story of a visitor that traversed billions of kilometers to intersect with human observation. The October 3rd Mars flyby, combined with Earth-based and space telescope monitoring, had revealed an object of staggering complexity. A coherent nucleus resisting gravitational and non-gravitational perturbations, a forward-facing dust halo defying conventional physics, and a chemical composition that stretched the boundaries of known natural processes. Each measurement served as both revelation and prompt for reflection, emphasizing the delicate interplay between observation, interpretation, and understanding. The potential implications for humanity were profound. If 3I Atlas were purely natural, it suggested that interstellar space harbors objects of greater chemical diversity, structural integrity, and dynamical complexity than previously imagined. The universe, in this view, was far richer and more intricate than assumed, challenging models of planetary system formation, interstellar object distribution, and chemical evolution. Every anomaly, from nickel-only emissions to CO₂ dominance, provided insight into processes occurring over billions of years, offering a window into environments far beyond the solar system. These revelations reinforced the importance of continuous observation, interdisciplinary modeling, and theoretical flexibility, urging scientists to expand the envelope of expectation while remaining grounded in empirical analysis. Conversely, if the object contained engineered features, deployed precursor probes, or exhibited controlled outgassing patterns, the encounter suggested intelligence operating at interstellar scales. Such a possibility redefined humanity's understanding of cosmic context, implying that advanced civilizations could observe, influence, or interact with emergent technological species in subtle ways. Even the mere plausibility of this interpretation invited reflection on the limits of human perception, the scale of technological capability, and the nature of interstellar communication and observation. The philosophical resonance was immediate. 3I Atlas forced consideration of the intersection between chance, design, and the observer's role in recognizing or missing extraordinary phenomena. Ultimately, the mystery persisted. Data from the Mars Flyby, perihelion monitoring, and multi-wavelength analysis provided unprecedented detail, yet the object's anomalies resisted simple categorization. The forward glow, dust dynamics, chemical spikes, hyperbolic orbit, and improbable alignment with planetary planes created a tapestry of observations that simultaneously pointed toward natural extremity and potential intelligent intervention. Humanity stood at the threshold of understanding, compelled to embrace uncertainty while deriving meaning from observation. In this interplay of empirical rigor, speculative thought, and philosophical reflection, 3I Atlas became more than an interstellar object. It became a lens through which to examine the universe, the limits of knowledge, and the profound wonder inherent in encountering phenomena that challenge the boundaries of comprehension. Its passage through the solar system would be fleeting, yet its imprint on human thought, curiosity, and imagination would endure, reminding observers that the cosmos is at once familiar, mysterious, and infinitely expansive. As 3I Atlas receded from the inner solar system and vanished behind the Sun, the pace of observation slowed, giving space for reflection and contemplation. The mysteries it presented, the nickel without iron, the forward-facing dust halo, the improbable trajectory, and the dynamic chemical shifts lingered in the collective consciousness of scientists and observers alike. In the quiet aftermath, the data transformed from raw measurements into a story, a narrative of an interstellar traveler whose passage had intersected human curiosity, skill, and imagination in a fleeting yet profound moment. The cosmos had delivered a visitor not merely to be catalogued, but to provoke thought, challenge assumptions, and inspire wonder about the scale, complexity, and potential intelligence beyond our solar system. Even as instruments ceased active observation, the implications remained vivid. Each spectrum, image, and trajectory calculation carried insight into processes spanning billions of years, from the formation of distant stellar systems to the subtle forces governing dust, gas, and metal in interstellar space. Whether entirely natural partially engineered or deliberately designed. 3I Atlas exemplified the extraordinary extremes of cosmic evolution, forcing humanity to reconcile observation with probability, physics, and philosophy. Its passage was a reminder that understanding the universe requires patience, rigor, and openness to phenomena that stretch the imagination, challenging both empirical science and the deeper questions of existence. In the softening glow of reflection, one could imagine the object continuing its journey, leaving behind trails of particles and memories of observation, its secrets preserved in spectral lines, infrared signatures, and the collective memory of those who watched. Humanity had glimpsed a fragment of the universe's boundless potential, a messenger from distant space carrying chemical, physical, and philosophical lessons. As the observational window closed, the mind wandered gently through the implications, the subtle balance of chance and design, the vastness of cosmic time, and the delicate interplay between discovery and understanding. And in that quiet, the universe seemed simultaneously more knowable and more mysterious, leaving a lingering sense of awe, humility, and the profound beauty of an encounter that would resonate long after the object itself had passed from view. Sweet dreams.